Today we will use the Kahn-Ingold Prelog rule to determine group priority for easy alkenes. We're starting with an original molecule. This is just a random alkene. And in order to find if an alkene is E or Z, we have to compare the priority of the two groups on each alkene carbon. I've highlighted both alkene carbons in red and blue, and that way it is much easier to do the problem later on. There are 3 easy rules to determine the priority for any alkene. So number 1, we branch out at the first atom of each alkene carbon and look for atomic weight difference. To begin, we're going to start with the red alkene carbon. The first atoms branching out from the red alkene carbon are both carbon and carbon. Since the atomic weight of carbon is 12.01 AMU, there is no atomic weight difference. So we move on to step 2. In this situation, we then branch out to the second heaviest atom and look for atomic weight difference. As you can see highlighted in pink, on the second atom branching out from the red carbon, we have a carbon at the bottom and a chlorine at the top. Because the second atom, chlorine, has an atomic AMU of 35.45, the top group of the red alkene carbon would be considered the higher priority. So now we have that labeled in red. If we go to the other side, to the blue alkene carbon, the first atom branched out is a carbon and a hydrogen. And because hydrogen has an atomic AMU of 1.01, we don't need to move on to look at the second branch atom. We can stop here. And because carbon's heavier than hydrogen, the bottom group of the blue alkene carbon would be considered the higher priority. Because the higher priority groups are on opposite sides of the carbon-carbon double bond, that would make the alkene an E alkene. What happens if we branch out the second atom and there's still no atomic weight difference? Do we go to the third atom? No, not necessarily. Let's take a look at the molecule below. It looks quite complicated, but don't worry, we'll go through this problem step by step. Now, we do not branch out at the third atom and compare atomic weight difference. Instead, for number 3, we compare the number of bonds to carbon from the first branched atom. Once again, I've highlighted the 2 alkene carbons we're focusing on in red and blue. That way it's easier to separate the groups later on. We start with step 1. We branch out at the first atom of each alkene carbon and look for atomic weight difference. So for the red alkene carbon, we see the first branched atom is carbon and carbon. Because the atomic weight is the same, we're going to branch out to the second atom, which is again carbon and carbon in pink. Now we go to step 3, which is to compare the number of bonds to carbon from the first branched atom. So here I have a brown arrow pointing to the original first branched atom, and this one has 3 bonds to carbon, as circled on the screen. Then we look at the other branched atom on the red alkene carbon, and notice for this one, there's only 2 carbons physically attached, which is the pink one and the red one. However, it has 4 bonds to carbon. The triple bond circled counts as 3 bonds to carbon, and the red one also counts as another bond to carbon, making a total of 4. Since the top black carbon has 4 bonds to carbon, that would make that entire group the higher priority. I'm following the rules of branching out at the first atom from the blue alkene carbon, so we both have carbon-carbon, atomic weight difference is the same. Then we branch out to the second atom, and there's still carbon and carbon, which is highlighted in pink, and the atomic weight difference is still the same. So now we go back to step 3, which is to compare the number of bonds to carbon from the first branched atom, and that would be the black carbons. The top black carbon attached to the blue one has 3 bonds to carbon. The double bond counts as 2, and the bond to the blue carbon counts as 1. The bottom black carbon has 2 bonds to carbon, making the group at the top the higher priority. Since the higher priority groups of the alkene carbon-carbon double bond are both on the same side, that would make that alkene a Z notation. Determining easy notation for an alkene is very easy. You only need these 3 rules highlighted in green. In conclusion, if both higher priority groups are on the opposite side of the alkene, you have an E version. If both higher priority groups are on the same side, then you have a Z alkene.